First up, it's Oskar Laverny. He's a postdoc in Belgium in UC Louvain.
Yeah,
and,
you pronounced it correctly.
Sorry?
You pronounced it correctly.
Perfect, yeah. I have a little bit of French training, so yeah. So his research interests are in high-dimensional statistics and dependence modeling, but you're actually an actuary by training. So we'll be talking about Copulas.jl. Thank you.
I have a half hour to talk to you about Copulas.jl, which is an attempt that I made a year and a half ago now to implement in Julia a set of useful tools for statisticians, which are Copulas. So the talk will be a little theoretical on the start. I'm going to give you a thorough introduction of what are Copulas, why are these things useful. And then we are going to talk a little about the implementations. I'll give you a few use cases that are already working, and I'll also give you a few glimpses of what's the future of the current implementation. So, a copula is simply defined as the distribution function of a random vector that has uniform margins. So it's a random vector in dimension d, which is supported in the unit hypercube, and its marginals are uniform. And in fact, there is this theorem from Sklar, which says that for any random vector x, if you write fx, the distribution function of the random vector itself, and fxi is the distribution functions of the marginals, then there exists a function c, which is unique once the random vector is absolutely continuous, that gives you these functional equations between fx and the fi's. Yeah, the notation is not the same on the top and the bottom, but yeah, you'll follow. This existence and uniqueness of the copula gives you a way to separate the problem of estimation of the distribution of the random vector into, on one side, the estimation of the marginals, and on the other side, the estimation of the dependent structure, which is the copula. This separation can be useful for a lot of stuff. You might have more information on the marginals than the copula. It might be the other way around. It's less common, but and also you might be able to construct a lot of parametric structures from parametric copulas and parametric marginals that are not from the same classes, and it gives you a freedom of modeling that is larger than what we have if we only consider multivariate parametric models. So a few comments. I just said that is that the function c describes and contains the dependent structure apart from its marginal distributions. And I have a few examples. The first one is the function pi, which is simply the product function. And this gives you a random vector which has independent marginals. And the two other ones are called Fréchéov-Dick bounds. And this is actually the minimum possible copula that you can have and the maximum possible copula that you can have pointwise. They represent full, complete comonotonicity between the marginals and full negative dependence between the marginals. And as for univariate distributions, of course, there are a lot of families, of parametric families that are known, and we are going to discuss a few ones right now. The first one is the family of elliptical copulas. This family is easily described by using the concept of spherical and elliptical random vectors. And we say that a random vector x is spherical if multiplying it by an orthogonal matrix keeps the distributions the same. Yeah. And then a linear transformation of this vector is elliptical. This is in fact the case for Gaussian random vectors. This is also the case for other random vector than Gaussians. You can think about students, for example. And then the elliptical copula is simply derived from these random vectors by applying the Sklar theorem that we just saw on the previous slide. So there are two main used families, the Gaussian and the student. But there is also the possibility in the package to provide your own elliptical generator and to do the same thing with another family. If you see that if you have a positive and univariate distribution, by making it turn around the center of the plane, you can construct a spherical random vector, and then from it you can extract the dependent structure. This is an example of a sample from a bivariate copula, the Gaussian one, with quite a high sigma, and so it's a sample on the unit plane, the unit square, and you see that there are more points in two of the corners, which means that the dependence is quite positive. When one of the random variable will be big, the other one will be big too. Yeah. Another class of copulas that is, how to put it, central in a lot of stuff that happens in finance, for example, is the class of Archimedean copulas. To define them, I first need to define the property of a function to be d-monotone. And we say that a function phi is d-monotone if it has at least d-2 derivatives, and the sign of the derivatives alternate. And the last one is non-increasing and convex, which means that the sign of the d-1 and d derivative also alternate, even if they don't exist. A function that has this property for all d, for example, will be called completely monotone, and these are functions that are really smooth. Like if you take, for example, exponential minus t, that's a function that is completely monotone. From this function, we defined Archimedean generators, which are d-monotone functions that are normalized to be 1 at 0 and to go to 0 at infinity. And then the function that is described as, there should be a -1 somewhere, C of u equals phi of sum of the phi -1 of ui's. There is a -1 missing. This function is actually a copula. It's a distribution function which has uniform marginals when phi is an Archimedean generator. This parametrization gives the dependent structure that is completely symmetric. You see that the sum gives everything, gives every dimension the same weight. So that's one important characteristic of those dependent structure. But also the parameter of the model is now a function. So we have a freedom that is a little bigger than, for example, with a Gaussian model where the only parameter is a matrix. So there are some classical parametric families of generators. The first one is e to the -t, which generates the independent copula, there is also the Clayton, the Gamble, the Frank, the Annie-Michael Heil, I think it's the name of the third one. I don't remember. And there is a lot of them. There is a paper from Nelson in 2006 that gives a very comprehensive list with more than 30 of them. Of notable generators that are used and that corresponds to model that people actually use by time to time. Okay. Those copulas are a lot less easy to sample than the Gaussian ones, right? To sample the Gaussian ones, you simply sample a Gaussian random vector, and then you apply the normal CDF, the normal inverse CDF to get back to the normal quantile function to get back to the unit square. Here it's a little more complicated, and in fact we have some decompositions that allow to sample them correctly, which is called the radial simplex decompositions. There is also another one that I will discuss a little less, which is called the frailty representation. And what it says is that the vector u that is following an Archimedean copula with generator phi can be decomposed. So the dots are exactly the broadcasting from Julia that you'll expect into phi of a product between a uniformly distributed random vector on the simplex. That's a random vector that will give you the direction in which the point will go in the space. And then R is a non-negative random variable that will give you how far it will go in the space, which should be independent from S. And in fact, there is a transformation that is called the Williamson transformation that gives you a mapping, a bijective mapping between the function phi and the distribution of the random variable R. And so from the generator phi, if you can compute this mapping, you can obtain the distribution of the random variable R, and then you can sample it, sample uniformly from the simplex independently, and then multiply the two, apply phi, and you get a sample from the Archimedean copula. There is also another representation which is used by the OR package, but which I don't use, which simply constructs not OR, but one over OR, which has phi as its Laplace transform. So it's not exactly the same transformation, but it might also be useful. The problem is that this one is only working when the generator is completely monotonous and not demonotonous, which is a kind of a restriction. And there is also on the bottom of the slide a few references for these representations. So here you have two examples. On the left, that's bivariate Clayton. You can see that the bottom of the graph is very dependent, and so the left side of the distributions will have a high dependency, but the right of the graph is a lot less dependent, and so the right side of the distributions will be independent asymptotically. And on the right, it's a Gumbel model in which it's kind of the other way around. You also see that the shape of the structure is not exactly the same. There is also the possibility to construct empirical copulas from data sets. And it's actually quite easy. You just need to take the ranks and then renormalize them correctly to obtain something that lives on the unit hypercube. And this application here that constructs the U's from the ranks of each marginals just renormalized gives you, if you take the empirical cumulative distribution function of U, that's the empirical copula of the x's. The problem with that is that this model is usually not a copula. It doesn't have uniform marginals. It's a discrete stuff. And so there are a lot of smoothings that exist in the literature. For example, there is the Bernstein smoothing, there is the beta smoothing, there is the checkerboard smoothing, and all of them can be useful and are implemented and can be used directly through this empirical copula stuff. Where you can pass it the x's or the u's as you want, and say that you want it to compute the ranks or not. So yeah, let's try to talk a little more about the implementation. In the package, we have a thing that is called the Sklar dist and the function fit that allows to do stuff like what's on the blackboard. I just load the packages. I defined the distribution for the marginals. I define C as being a given copula. And then the Sklar dist constructs the vector D that is just applying the Sklar theorem, which has as a dependent structure the copula C and as marginals x1, x2, x3. I can then sample it like you'll sample anything from Distributions.jl. It's a proper continuous random vector from Distributions.jl. You can also fit it directly by passing to the fit function the type that you obtain. So it's just Sklar dist of the name of the copula and a tuple containing the name of the marginals. And then you pass it the data and it will fit it. Here the copula is not the right one. The marginals are the right one, so the fit might be really bad, but it's working. And we actually comply with what Distributions.jl said in its documentation, which is that the fit function will choose a reasonable way to fit the distribution, which in most cases it's maximum likelihood estimation. So here, what we do is that we use the fit function from the marginals from Distributions.jl, and then on the residuals from those fit function, we use whatever we want to fit the copula. For the Gaussian and the elliptical ones, it's actually maximum likelihood. But for the Archimedean one, it could be maximum likelihood, but for the moment, it's a moment matching algorithm that runs in the background. So this is practical. This is something that is on par with what is available in the OR package, which I kind of translated into Julia to obtain this kind of behavior. About this translation, Here is the actual implementation of the Clayton Copula in the package. It's just a few lines. And then the infrastructure around it to define the Archimedean copula is not that big either. And if you want to define your own Archimedean copula, it's actually quite simple, right? You just need to tell it what's the generator, the inverse of the generator, what's the tau. I did not describe it, but it's a dependence measure, the Kendall tau, the inverse of the Kendall tau, and then you need to give it the radial distribution, the distribution of R. The equivalent in the R package is hundreds, thousands of lines of codes, right? The API for the Archimedean stuff is moreover quite modular in the sense that from these functions here, you are not obligated to provide everything. If you provide only phi and phi inverse, you will be able to compute the CDF, the density, and a lot of stuff. If you provide only the radial dist, you will be able to sample from the distribution. And what else? Yeah, and that's what I was saying earlier. If you want to fit it, you need to provide the inverse tau because that's what I'm currently using to fit it. But actually, if we implemented correctly the Williamson transform, which I didn't do yet, you could even fit it through maximum likelihood by just providing phi and phi inverse. Yeah. So even if you don't know much, about the Archimedean family that you want to use, it's still possible to do stuff and to leverage the architecture that is already here to fit it correctly, to sample from it, blah, blah, blah. So I have a few usage examples that are directly coming from the fact that we hook into Distributions.jl infrastructure. And the first one is that Turing works straight out of the box without doing anything, which is kind of spectacular because to do those kind of stuff in R, it's a pain. Here I just have a Turing model with a few prior for some parameters. There were more in the model that I used, but the screen is not big enough to put too much stuff, so I reduced it to a bivariate model. And then there is the distributions of the marginals. We define the copula. We define the Sklar distributions, and we just call Turing.addLogProb to add the log likelihood of the model. And even the log likelihood function is not one that I programmed myself. The log likelihood function is coming from Distributions.jl. I had nothing to do to make it work. This is possible to fit a model in a Bayesian context. So you'll get samples of the parameters, and you get uncertainties and stuff. But it is also possible to fit models that are more complicated in Turing, for example, regression models, where the residuals are following, while the residuals might not be just standard Gaussian, they might have some dependent structure that you fix beforehand into one of the parametric families, and then Turing works its way and finds the right parameters. This is something that is impossible to do in R, and here it's free. Another example that I really like is called globalsensitivity.jl. It's not mine. It's just that those guys needed to implement some things called Shapley effects, which are a way to model the influence of the inputs of a black box model onto the output of this model, and a little better than what Sobol effect might do. Sobol effect is the Gaussian version, and Shapley effects are the version with a dependent structure. And so they just hooked into Copulas.jl and implemented their stuff. And if you look at the documentation, I did not put the code on the screen because it's a little long, but it's actually a pretty nice piece of code. There is also this one, which was a little less expected. And there is this guy called Alec from Julia Actuary that actually used Copulas to correlate Black-Scholes models when he samples some stocks, and to abilide using several stocks that are independent from each other, which is an hypothesis that is probably completely wrong. He had this thing called correlated, where you just pass the stocks and you pass the dependent structure that you want, and it produces stocks that are correlated, which residuals are correlated. with these dependent structures, of course. This is also something that is hard to do in other languages. Yeah. I don't know why it says "or the future" here. Yeah, I'm starting to arrive to the end of my slides. There is potentials for other integrations with the current state of the field. The one that I really like is probability bounds analysis. It's a package that assumes the fact that you don't know the dependent structure between your random stuff, and it will give you bounds on, for example, the sum or the maximum or stuff like that, assuming that you don't know how the things are correlated with each other. And it's a pity because they came before Copulas.jl existed, and they actually re-implemented a lot of stuff. Well, I re-implemented a lot of stuff that I already had. And we have a plan. There is a pull request to remove this duplication and actually use the Copulas.jl stuff. And there is also fuzzylogic.jl. 3 days ago, I stumbled upon this guy called Luca at the registration desk, and he told me about this fuzzy logic stuff. And fuzzy logic is a field where you replace the AND function on the standard logic by what you call a T-norm, which is a fuzzy AND. And in fact, copulas are T-norms. And we took a look, and in fact, it will be possible, and we plan to do in the next few days or months maybe to hook into Copulas.jl so that he can use the parametric models that we have to produce fuzzy logic T-norms. There are probably others. If you have some, I'm all ears, of course. And there is also some potential for future developments of the package. This is things that I don't really have the time to do right now, but which I am supposed to do. The documentation is not comprehensive enough, of course. It's never. There is a lot of models that I want to add. The hierarchical Archimedean copulas, the Vine constructions might be really nice to have too. And there is also some kind of dependence metrics that I did not define and that I did not talk about here, which might be interesting to add to the package. And yeah, there is also the problem of estimators because those models are maybe harder to estimate than what we already have with the maximum likelihood and the moment matching stuff. Of course, if you find some missing functionality, do not hesitate to come to me. Voilà, thank you very much for taking the time to listen to me. And if you have questions, I'm all yours.
Okay, yeah. For the questions, I'll pass on the microphone to you.
So I know you mentioned fitting, using it to fit data into a Copula. Do you also have ways to simulate, let's say, simulate a Copula based off of parameters?
Yeah, we have the two. We have the rand function from Distributions.jl that works and that samples from the Copula, or from the Sklar distribution. It's the same thing. You can put a C instead of the D in the rand function. It works. That's for sampling, and for fitting, we simply hook to the fit function from Distributions.jl. Yeah.
Also, is it type stable?
Yes.
Okay.
I bet so. I hope so. Yeah, for the moment, it looks like it's type stable. Yeah.
I have a question. Have you tested it with the high-dimensional copulas?
I can't hear you.
Can you hear me?
Yeah, it's
okay.
better.
I'm wondering how your package performs with very high-dimensional copulas, like 50-dimensional, 100-dimensional, because even with the simplest independence copula, if you multiply 50 numbers between 0 and 1, you get numerically 0. So have you tested that?
Yeah, that's actually a very good question. It depends on the model. For the elliptical ones, the fact that the dimension is big is not very a problem because we we use what's already available for high-dimensional Gaussians and high-dimensional students into Distributions.jl, so it works quite correctly. For the Archimedean ones, for the moment, I had no issues with that. There is this algorithm to sample the density. I think I've not the, yeah. To sample the density, to compute the density of the model, you actually need to derive this function phi d times, d being the dimension. And this derivation can be done in the R package. It was done by hand until d equals 8, and then your facts. But what we did here is that we used forward diff, and forward diff can actually go pretty far. Yeah. So I pushed it to 20, 50 I did not try. But the thing is that for higher dimensions, usually you don't use those copulas directly. And for higher dimensions, what you want to do, if I can't find it, is actually Vine's copula, which is a way to imbricate the copulas, the one with each other. And so you only have to define and to use bivariate models to construct something that can be high dimensional. But this is not implemented yet, right?
In R, they get around having to multiply the money by. Okay. In R, they get around having to multiply numbers that are very small by computing the log CDF or something like that. So yeah, so
yeah,
yeah, so
you can get by Turing. Add log prob.
Yeah, so okay. Turing computes the log of the density. The thing computes the log of the density, not the density itself, of course.
Why do you use add log prob instead of tune for?
Because it doesn't work.
Why doesn't it work?
I don't know. It's a very good question. There is actually, no, that's not, no, I'm sorry. There is a Discourse thread that's not on the thing that discusses that with the people from Turing. But yeah, if you have a good idea for what it doesn't work, then...
The thing on the face of it, it should work.
Yeah, but it doesn't. Okay. I don't know why.
What was the question that you just answered?
Oh, the question was why I'm using add log prob and not directly the tilde from Turing.
Oh.
And the answer is that because it doesn't work, and I don't know why.
Do we have any more questions? I'll try to get to you. Oh, can we pass the mic back?
My question is about the definition of the Archimedean copula. So I guess that this is an important definition because it allows you to, I guess if you have an Archimedean copula, you know that it's going to be simpler to sample or estimate. What do we gain by knowing that a copula is Archimedean? And it seems to be quite an important definition.
Yeah, so first of all, the definition is wrong. This should be phi minus 1 and not phi. This one here should be phi minus 1. Why it's an important class? It's because the function C is a function from 0, 1 to the D into 0, 1. So you have a big space, which is 0, 1 to the D, in which you need to do stuff. And here we reduced that onto the estimation of a univariate function. And this reduction is interesting because you may be able to use information from all the dimensions to compute this univariate function, right? And so yeah, that's why the class is so used in the literature.
Okay, I think that's all we have time for. So let's
thank you very
Oskar
much.
Again.